Welcome to the class. We're going to start in a minute or so. Can you all hear me? Welcome, good sir.
Hello.
Welcome, Benice.
Hello.
So we're going to talk English as much as possible. Benice joining us, good sir, but she found the Afrikaans syllabus too easy, and that she switched over to English syllabus because it's harder. Okay. Does that make sense? No, it doesn't. Because it's not the truth. You are Afrikaans, Benice, but you've been schooling in English like since when?
From preschool.
From preschool. Okay, so you are English. Right. So the suggestion was made. Remember, I don't always ask you this, but when I send you out the link in the morning, you must just respond back and say, thanks, we are doing this or that at the moment. It makes it easier for me just to get the stuff ready, so I don't have to, while the lesson is on, try and find the stuff that you're doing. So the suggestion was made that you are doing organic reactions. Is that true?
Yes.
And Kutsa, what are you doing? Mr. Kutsa, what are you doing at the moment? Hi. Okay, just plug in your mic again, Kutsa.
Yeah, it's in now.
Good. What are you busy with at the moment in physical science?
I'm still busy with organic molecules.
Okay. Last time, I can't remember how far we got, but we were naming up till alcohols. Is that correct?
Yes, I believe so, yeah.
So we haven't done carboxylic acids. We haven't done esters. Or have we done? We have done esterification. Yes. We haven't done, we haven't named organic aldehydes, ketones. We haven't named esters. We haven't named carboxylic acids. So if you have any questions with regard to the naming of those molecules, you must ask me. Or what we can do, we can look at the organic reactions, because that's the most important part of your organic syllabus. And then we can leave 10 minutes at the end just to make sure that you can name your carboxylic acids, esters, ketones, and aldehydes. Those things name really easy. A carboxylic acid is the easiest thing to name, and esters is slightly harder, but ketones and aldehydes really easy to name. So I don't really want to waste a lot of time on that. I'd rather be starting with organic reactions. Are you happy with that?
Yeah.
Okay. Right. Now you have to focus. There are three main reactions: addition, elimination, and substitution reactions. You are going to do polarizations also, polymers. And you're going to do combustion reaction. But we're not going to look at that. That is very, very, very seldom that counts a lot of marks, and it's part of your theory that you're going to learn without me helping you. We simply don't have time to go through everything. So basically what I do in these classes, one, my priority is to help you with stuff you're struggling with. So if you've sent me any examples, or you want to send me any of the examples you're struggling with, you do that now via a WhatsApp photo. If you don't have my number, give it to you. But the easiest way for me to help you with a specific question you have is just to send me a WhatsApp with a photo of the question, and then we just do it here on the whiteboard. So my priority is to help you with current questions you have. Secondly, my priority is to help you with certain parts of the syllabus that requires a lot of understanding. I'm not here to help you with definitions. I'm not here to help you with theory, because that is not why you are here, because you can actually study it. I'm here to help you with stuff that you need to understand. So we're going to look at the organic reactions. We're going to look at addition, elimination, and substitution reactions. And those are extremely important, and they count a lot of marks. So just a quick overview. An addition reaction occurs when we start with a double or a triple bond. You're basically not going to see triple bonds, so I can just ignore that for now. When you start with a double bond and your action ends with a single bond. All reactions that start with double bond, ends with single bond, are addition reactions. An elimination reaction, we're going to start with a double bond and we're going to end with a single bond. So any reaction that you see that your reactant is a double bond and your product is a single bond, you know it's an elimination reaction. And then substitution reactions, you start with a single bond and you end with a single bond. So those are a nice overview. So you exactly know what type of reaction you're busy with by just looking at the reaction. Starting with double, ending with single is addition. Double to single is elimination, and substitution is single to single. So that's very easy to remember. Think of any sport, like hockey or whatever. If you add someone to the team, you're going to have more players. Now, more players means if I started with a double bond, I only have 4 hydrogens. If I end with a single bond, I have more hydrogens, so I have more players. An elimination reaction, look at this. I did it the wrong way around in my elimination. No one stopped me. Elimination reaction, you start with a single bond, you end with a double bond. So you start with more hydrogens and you eliminate some of them. If you are eliminated, you don't exist anymore and they are gone and you have less. And substitution, you start with the same value, you end with the same value. So in a like a hockey game, if you substitute a player, say for instance you've got 11 players on the field. If you substitute a player, you still have 11 players. But if you eliminate someone, then you have less. Can you hear me, Benice?
Yes.
Wonderful. Okay, let's start with addition reaction. Okay, first thing we need to encounter is something called Markovnikov's rule. I don't know if you've looked at that. Okay, good so you haven't looked at it because you haven't done this part of the chapter. But okay, I'm going to give you Markovnikov's rule, but you don't have to memorize that. You don't have to understand it. I'm going to give you a shortcut how to understand Markovnikov's rule. Markovnikov said, in the addition of a polar reagent like HX just means any hydrogen bonded to a group 7 element. X is a group 7 element. That is a polar molecule. Or so any addition of a polar reagent like HX to an alkene or an alkyne, so a double bond, you're not going to work with alkynes now. So any addition of a polar reagent to an alkene, to a double bond, what happens then, the hydrogen gets attached to the carbon with the more hydrogen substituents. So that hydrogen in that polar molecule is going to attach to the carbon that has more hydrogen. And we call this the rich gets richer. Who of you have heard this? The rich gets richer. So the one with the more hydrogens gets more hydrogens. The one with the least hydrogens, you're going to find it's going to lose these hydrogens. Okay, let's start here. I'll explain. The only thing that you need to know about Markovnikov's rule, Markovnikov is like he's the rich Russian. He says a rich person gets richer. Good. Let's start. The first type of addition reaction that we have to learn is called hydrohalogenation. Right. So I don't know if the screen is big enough. Can you see what's happening here?
Yes.
Good, sir?
Yes, I can.
Okay, I'm just going to slightly make that reaction bigger. So here on the left is my alkene. Let's quickly name that alkene. Anyone. Give me a name. It's got a double bond, so it will end with ene. It's an alkene. It's got 4 carbons, so it's but. But I have to tell you on which carbon the double bond is. 1, 2, 3, 4. It's on carbon 1, so that is called but 1 ene. Just give me a second. Just give me a second. I'm picking up something. Just write that down. All right, maybe you want to take a screenshot or just quickly dot that down. That's called but 1 ene. I hope you can name that molecule. And I'm adding hydrogen bromide. Good. So that's a polar molecule. I'm adding that polar molecule. And look at the double bond. I'm just going to quickly explain what happens here. I'm going to redraw that but 1 ene. And I'm going to open the double bond. So I've got 2 hydrogens on the right-hand side carbon. I've got 1 hydrogen on the left-hand side carbon. So these 2 legs here are just an indication of what happens when that double bond opens up. Now, Makofnikov rule says you don't have to learn the rule. You just need to remember that the rich person gets richer and the poor stays the same or get poorer even. So which of those 2 carbons, the one on the left, I'm highlighting in red now, or the one on the right has the more hydrogens? It's the one on the right. So that hydrogen attaches to that one. It gets richer. It gets the hydrogen. He has the most hydrogen, so he gets the hydrogen. And then it's because the other one is more electronegative. The other one is basically positive, that this one goes there, the bromide goes there. Do you understand what happens? That's the mechanism. Okay, so the rich one gets richer and the other carbon just gets the halide group. Okay, this is a tertiary alcohol halide. Let's look at the bottom reaction. Right, let's quickly name that organic compound. I think the numbering is going to work like this: 1, 2, 3, 4. That gives my double bond the lowest possible value. Or 1, 2, 3, 4. Red numbers or green numbers? The red and the green numbers both give the double bond in number 2, but the red numbers gives the substituent a lower value. It gives my alkyl substituent a number 2, while the green numbers gives it a number 3. So the green numbers are wrong.
Mhm.
Name 2-methyl what? Butene.
Butene.
Yeah. Boom. Okay, you have to be able to name that. Okay, I'm adding that polar molecule. So let's open up that double bond before we just get the answer as is. The double bond will open. Let's draw all those 4 carbons. And there's my substituent. Okay, I'm just opening the double bond there. Now the carbon on number 3 has got 1 hydrogen. And the carbon on number 4 has got 0 hydrogens. So the rich one is the one on number 3, that one, or this one with the 1 hydrogen. He's going to get the hydrogen, and the bromine group is going to go on that carbon. So there's the answer. And we can name that if we want to. That is 2-bromo-2-methyl. You can say methyl if you want to. Butane. Does that make sense?
Yes.
So this is addition reaction, and this is called hydrohalogenation. And that difficult name of hydrohalogenation, you can just deduct from what you're adding. You're adding a hydrogen and you're adding a halogen. Halogen is a group 7 element. So what are we adding? Okay, it's addition reaction. If they ask you what type of reaction it is, you say addition or addition reaction. If they ask you what type of addition reaction, then you have to specify. Then you just look at what you're adding. I'm adding a hydrogen. I'm adding a halogen. So it's hydrohalogenation. Next one is the one you cannot get wrong. It's impossible to get it wrong. This is called halogenation. It's addition and halogenation. Quickly, I'll show you why you cannot get it wrong, because even if I open up both, I'm just going to put the hydrogens in there, open up both, open up the double bond, so both of those carbons have additional bonding area, then there's only 2 chlorines I can add, and there's 2 spaces for them, so I'm adding chlorine there and the chlorine there. So halogenation, you cannot get wrong, even if you try. Then your book might give some other stuff to add, like heat or something like that. So in this reaction, I know that there's actually no water present. So you don't have to say that, but if I ask you, what type of reaction conditions are there? You say, okay, you're not allowed to add any water. Adding a water would give you a hydroxyl somewhere. So there's not allowed to be any water there. Okay, that you'll learn. That's part of your theory. Okay, let's look at hydronation. Hydration, actually. It's not hydrate, it's hydration. What is to hydrate? What does it mean to hydrate? It means to drink water. So
Yes.
look at this. I've got a double bond. I'm ending with single bonds. So this is a addition reaction. And I'm adding water. So I'm hydrating. Okay, for water to function or to be part of the reaction, actually have to add a catalyst in the form of an acid. So you have to add a strong acid. You can either one of those 2 acids you can add, but you can forget about this one because hydrogen sulfate or sulfuric acid is a catalyst you can always use. That is your catalyst. You don't have to understand the mechanism how it works, how it makes this thing electronegative, or how does it help for the reaction to take place. You can just know that I'm adding water, so I'm hydrating. Let's open up, before we look at the answer, let's just open up those double bonds. So the carbon on the left has got 2 hydrogens. There's its bond. There's the 3rd carbon. So I'm going to just push that hydrogen to the bottom. So there's my 2 open areas that I can actually have bonding now. So Makofnikov said, look at those 2 carbons. I'm going to highlight them in red. Look at those 2 carbons. Tell me which one is the richer one. It's the one on the left. The one on the left's got 2 hydrogens bonded to it. The one on the right only has 1. So the one on the left's going to get a hydrogen. It's going to steal that hydrogen. And then there's a OH group left, hydroxyl group left, and that one will attach on the other carbon. So that becomes an alcohol. So we have prop-1-ene. You can also just call it propene because you can't have prop-2-ene. And that's adding water. And then this alcohol here is a secondary alcohol. And it's called what? Propan-2-ol. That alcohol. Right. Okay. Secondary alcohols are more stable than primary alcohols. Therefore, this primary alcohol will not form. Primary alcohol means the hydroxyl group would have been on the carbon on the left. That one's not going to form. So this is called hydration because you're hydrating, you're adding water. And water is always added with a strong acid as a catalyst. And then we have hydronation. Hydronation means we're adding only hydrogen. Okay. This one you cannot get this one wrong. The only thing you can struggle here with hydronation is is part of your theory. So in other words, what type of catalyst do I need to add? And what is the condition of the reaction? So if we open that double bond, there's only a hydrogen that can be added to the one and a hydrogen to the other one. But you have to add a catalyst. Basically, what I would recommend, just remember platinum as a catalyst. You're going to use that a lot later this year. So platinum is a catalyst, and how it basically works, it's a non-reactive metal. So there's a metal strip of platinum that put into this reaction. And the hydrogen gas, that's hydrogen gas. That hydrogen gas bubbles goes and it sits on the platinum plate. It goes and sits there in gas molecules. And that allows them basically to react with this alkene. Okay, but this alkene needs to be dissolved in a non-polar solvent first. So we take something like a carbon tetrachloride, you dissolve that alkene in that, and then you bubble the hydrogen gas through the solution and put a platinum little plate in there so that the gas can actually get stuck on that plate and it allows for reaction to take place. So this one is a bit theory that you need to add. Okay, and that concludes your addition reactions. Okay, there's nothing difficult at the addition reaction. Some of the harder ones are within substitution and elimination reaction. Okay, let's do substitution reaction. Substitution reaction, you start with a single bond and you end with a single bond. These reactions normally takes a slow reaction time. It allows for one atom, like a sulfur bromine atom, to be divorced from the chain and then replaced by something like a hydroxyl or something. So the reaction conditions allows for not a very quick reaction, slower reactions. You don't need to know that. Okay, first one, hydrohalogenation. Let's just see what does the word hydro mean? It's hydrogen. Halogen is group 7 element. So we're adding a hydrogen and we're adding a group 7 element, a halogen. Okay, now I've got an alcohol there. Okay, I'm looking at my reaction and it's single bonds ending in single bonds. So that's replacement or substitution. And I think it's really basic, not very difficult. What is happening? This hydrogen reacts with that hydroxyl group. It forms water. And that means that carbon there has now 2 valence electrons. And that bromine group, which makes this one the hydroxyl group was removed. Let me explain it to you rather this way. A hydroxyl group, OH, is 1 minus. That you know. If I remove that, this part of the chain is going to be more positive, and that bromine group is going to go and attach because bromine is Br1 minus 1. You don't have to know this. It's just for interest. You don't have to understand this. All you need to know, I'm substituting the hydroxyl group with a bromine group. Good. I want you to name, any questions?
No.
This is sort of easy.
I have a question.
Yes.
When it comes to maybe I'm wrong with this, but then with the substitution, you substitute the alcohol with the bromine.
Yes.
But I don't know if I heard this correctly, but if it's substitution, why is there also an addition of hydrogen and oxygen?
Oxygen. Oh, this hydrogen. Yeah.
Yeah.
Okay, that's just because that hydrogen has to bind with the bromine. You can't just put ions in there. So you have hydrogen bromine, which is an acid. Basically, it's something you can add to that product, to that alcohol. So it's a liquid, and that hydrogen needs to be, because it's hydrohalogenation. You can't just add Br1 minus ions. It won't react.
Oh, okay.
In other words, you can't just lose that hydroxyl group and make it float around here. That hydroxyl group needs to become water. And for that hydroxyl to become water, that hydrogen needs to be present. Otherwise, you won't get a substitution reaction. You'll get an elimination reaction.
Oh, so that's what substitution is. Okay.
Yeah. Okay, look at this also. This is called a tertiary alcohol. Look at the left, on the left. Can everyone see that this alcohol on the left is tertiary? Tertiary means that the carbon that the hydroxyl is bonded to, that carbon is bonded to 3 other carbons. That makes it a tertiary alcohol. Small, you can write it like that, 3-0. I'm not. And this is just room temperature. If it was a primary or a secondary alcohol, then you have to heat it up because otherwise it won't react. So look at that. That is a primary alcohol. I know it's primary because the carbon that's connected to the hydroxyl group is only connected to 1 other carbon. That's called primary. And if you take a polar molecule, so if we do hydrohalogenation, hydro and halogen added, then you have to add heat because otherwise that reaction won't take place. So that's a reaction condition for primary alcohols and secondary alcohols. Hydrolysis, next one. Okay, this is a very, very, very important one. And this is the one of the problems, the one that gives a lot of problems. I'll show you just now. Okay. Hydrolysis means what? I'm adding basically a hydroxyl group. Okay. So now I have a single bond, and this is called 2-chlorobutane. I'm adding a strong base. A strong base. How do I know that sodium hydroxide is a strong base? How do we know that? How do you know when something is a strong base? It's got a group 1 or group 2 metal that's bonded to a hydroxyl group. Group 1 and 2 metals, like potassium hydroxide, beryllium hydroxide, lithium hydroxide, sodium hydroxide, all of those are strong bases. There are a couple exceptions. Calcium hydroxide is also recommended as a strong base, but it's not that reactive. But anyway, you can just remember group 1 and some of group 2 elements connected to the hydroxyl group is a strong base. So we have got a strong base there. But that strong base is diluted in water. So they normally write it like something like this. NaOH, AQ. What does AQ mean? Diluted in water. AQ means aqueous solution. So they've diluted that in water. That means this reaction takes place, but it doesn't take place at a high reaction rate because it's diluted. That gives enough time for a substitution reaction to take place. If it was not diluted in water, but just concentrated, then you will not have a substitution reaction. And we need to put a little bit of heat there. I'm pretty sure there's heat added. I don't know why I don't have heat there. I'm just going to double check why I don't have any heat there. Maybe if you have a textbook with you, you can tell me why this one doesn't have heat. No, it doesn't have heat. Low temperature. Low temperature. I'm not going to add the heat. It's just a low temperature. Okay, good. Right? There must be indication of the fact that the strong base is diluted in water. This thing, they will also dissolve in ethanol. Okay. But that's part of theory. Are you with me? This is a difficult reaction. It's substitution. So what happens? Basically, that chlorine group, the reaction is not difficult, but you'll find now, I'll explain now, and I'll show you an example, and then you'll find, okay, you don't know which one it is. Is it now substitution or elimination? So that chlorine groups are just substituted by the hydroxyl group, and the chlorine are stolen by that, what's it, sodium. Why? Sodium ion is +1 and a chlorine ion is -1. They bond very, very nice, very quickly. They love one another. Will you be able to do this? This one has a little star because that's a very important one. Next one too. The next hydrolysis reaction is the addition of water. Okay. Substitution reaction. We have a primary alkyl halide or haloalkyne. Just you can name it whatever you want. Or you can use any one of those two names. You can use haloalkyne or alkyl halide. Right. What are we adding? We're adding water. So basically, nothing difficult. That chlorine is just going to be replaced or substituted by a hydroxyl group. You have to learn this one. The chlorine comes off and it binds with that one of those hydrogens. Both of these are called hydrolysis. Alcohols are formed. Okay, last one of the substitution reaction is called halogenation. And this is tricky one. Okay. We have butane there. It's a saturated carbon bond. Okay. It's an alkane. And now we're adding ClCl now. And this, you can use UV light, I think. So now the question in exam is, are only one chlorine attached to that or two? Remember, you can get confused with the reaction there and this reaction plus Cl. In the reaction below, we have a addition reaction. Both bonds will open. Both of those bonds will open and both chlorines will attach in this addition reaction. But in our substitution reaction, where we're not starting with a double bond, but with a single bond, only one of the chlorine atoms are going to bind. Okay, now the question is, where does it bind? Because if I'm going to make space now everywhere in that chain for chlorines to bind. I'm just going to put in all the hydrogens. And there's 1, 2, 3, 4 areas because that chlorine can go anywhere. Okay. So you either want a tertiary or a secondary or lastly a primary alkyl halide or haloalkane. So the chances of the chlorine binding on any of the ends is very, very slim. It will be only like 40% of your product. You'll have primary alkyl halides. So the chlorine will bind either on the second or third, roundabout as far as possible or as near as possible rather to the middle of the chain. Because now I have a secondary, what? Haloalkane. And a secondary haloalkane is more reactive and it forms in greater quantity. The secondary or tertiary alkyl halide or haloalkane is more reactive and will form in greater quantity. But let's say, let's check just a figure. This one will be around about 70% of your product. But you will also find, if you do this experiment, that you will have primary haloalkanes. So you also have a primary alkyl halide or haloalkane. And this one will be like 30% of the product. But this is the one that you need to write in the test. not the bottom. Okay. I want you to take note of this. This is very important because in your exams, you might find that you get this reaction, and then they have this answer, which you don't understand. Why? How can I have that primary haloalkane? It's not the product that forms in greater quantity, but it also does form. So you can use that as an answer, or not use. They can use it as an answer to get us another, because they have a flow diagram. I don't know if you've seen what it looks like. It's a flow diagram. So you have to work from this one to another answer, and they might use that one. Just take note of it. It does form, but very small quantities. Good. Elimination reactions. Okay, Zaitsev's rule. Again, we have a rule here that you don't understand and that you don't have to learn. I'm just going to make it slightly smaller, or bigger rather. Okay, Zaitsev, that's the poor Russian. We have the poor Russian. I think they are like Ukrainian or Polish or something. Zaitsev's rule says the alkene, okay, let's just start here. Elimination reaction, we start with a single bond and we end with a double bond. So the alkene, the double bond, formed in greatest amount. So the greatest amount, the product that will form corresponds to the removal of the hydrogen from the B carbon having the fewest hydrogen substituents. Now that doesn't gel, unless you exactly know what he's saying. But you're not required to know this rule. So I'm just going to say Zaitsev's rule is the poor gets poorer. So the poor gets poorer. Do you understand that? What does that mean? The person that doesn't have money gets less money. Or in organic terms, if I can call it that, the carbon that has the least hydrogens will also lose a hydrogen. So if you look at two carbons, what they're doing is they look at the double bond. They look at three carbons. Say, for instance, I have a hydroxyl group here that I'm going to eliminate. Then they call it B carbons. So this is the primary carbon. This one is attached to the hydroxyl group. But around that carbon, I have B carbons, carbons that is attached to that specific carbon. Now, the B carbon on the right has 3 hydrogens. And the B carbon on the left only has 2 hydrogens. So Zaitsev said, basically, there will an alkene will form that corresponds to the removal of a hydrogen from the B carbon. In other words, one of these hydrogens will be removed from one of those 2 blue carbons. And we can remember it as the poor one will lose its hydrogen. He just says they will form an alkene that is the most substituents. I'll show you now. So I think I know I think you know already what's going to happen. Okay, I'm just going to rewrite those 3. 3 is 4. Sorry, it's 4. It's 4 carbons. One not use 3. So let's just write those 4 carbons. I'm just going to redo that. So, sorry, can't hear you. Who's that? Denise, are you fine?
Yes, I'm fine.
Okay. I'm just going to redraw that structure. That hydroxyl group is now going to disappear. Now that double bond can either fall to the left or to the right. Now our rule says the poor one will get poorer. So we're going to look at these 2 green carbons and ask which one is the poorer one. It's the one on the left. It's got 2 hydrogens bonded to it, and the one on the right's got 3. So the one on the left will lose one of his hydrogens, and the double bond will form in that way, towards that one. Now, Zaitsev said the alkene will form that has the most substituents. Now, what he's actually saying is this alkene, if you look at the double bonded area, This double bonded area has two substituents, two sides. If we took the double bond and made it stuck on the right-hand side, the alkene will look like that, and that alkene will only have one substituent. This is a less stable structure. This is called your secondary product. This is not your main product that forms. I'm going to draw it in another way, just to explain it to you. So if you study organic chemistry next year, you won't draw it like this. Your molecule will look like this. There's your molecule. And the one on top will look like that. So this is your primary product. And that's a secondary product. Now imagine you take these two molecules, the one at the bottom, and you spin it around, because they don't stay still, they spin around. Can you see that the spinning of this molecule, the movement of this molecule is more stable? Because it's got in the middle of the molecule, it's got that axis that it can turn on. While this one on top, if this one moves about, then it's not balanced and it will not move in the same way that the bottom one will. So the bottom one will be, will have a higher percentage of the primary product than the secondary product. So this is your main product that forms. Okay, let's see if we can actually apply that. Okay, very, very important. Very important. This one is very important. You always get this one. I'm starting off with 2-chlorobutane. 2-chlorobutane. I'm going to add concentrated base. Okay, so that's a base. That's concentrated. Look, there's no water anywhere. And I'm dissolving this in ethanol first. If there's a diluted base, remember, if we have NaOH diluted in water, that will give a substitution reaction. But now this base is not diluted in water, it's concentrated. Once it's concentrated, we'll get a very quick reaction, and that will be an elimination reaction. There's your primary product, and there's your secondary product. Let's try and explain that. There's my 2-chlorobutane, carbon, 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 carbon. There's the chloro. That one is removed by the sodium and becomes sodium chloride. And now the double bond can fall either to the right or to the middle. If it falls to the middle, to the right-hand side has 3 hydrogens attached to it, and the left-hand side's got 2 hydrogens attached to it. So it will fall towards the middle, and this hydrogen will be removed. Okay, this is called D. D means remove. Hydro, I'm removing the hydro, and I'm removing the halogen. Okay, what does decapitate mean? Good, sir. Decapitate. It means to chop off someone's head. So DE just means the removal of. I'm removing. So elimination reaction starts with DE because it means remove. I'm removing the hydrogen and I'm removing the halogen. Let's do that reaction again. A fresh one, a new one. Okay. I have, say for instance, I have, let's make this a long chain. So I'm going to put let's say iodine here. Any alkyl halide. I'm going to put in all the hydrogens for you. This is tedious, but it's got to be done. Okay, I want to remove that iodine in an elimination reaction. One of the ways of doing it, or the only way that you're aware of, is to add a strong base that's concentrated, not diluted. And I'm going to dissolve that in ethanol. What that strong base means it removes and the reaction takes place quickly, so no substitution can take place, only elimination. So basically that sodium that is +1 rips off that iodine from that chain. It just takes it. It becomes sodium iodine. Okay, and that means there's a bond open. I'm going to rewrite off now. Done myself in by making such a long chain. So this bond here is open. The iodine's gone. Now, this is going to fall either to the left or right. You can either make the double bond to the left or to the right. The carbon on the right's got 3 hydrogens attached to it. The carbon on the left has only got 1 hydrogen. So Zaitsev said that carbon will lose its hydrogen. So there's a hydrogen that comes off, and the double bond forms there. The double bond will always fall towards the middle of the chain, as far as possible towards the middle, as near as the middle of the chain as possible. So there's also hydrogen gone, and there's the sodium is gone, and that hydroxyl group will bond to the hydrogen to form water. So what did we take away? We take away halogen, and we take away one of the hydrogens. So it's dehydrohalogenation. We take away the hydrogen and the halogen. This is a very important reaction. Very important. Okay. You can photograph that one if you want to. I'll just take off some of this stuff I put in here. It must be a strong base and must be concentrated. This is just Afrikaans. I'm just going to scrape this out. With a new product. It's like your primary product and secondary product. 2 reactions left. The next one is dehydration. What was hydration again? To hydrate means to add water. So dehydration means I take away water. Right. To take away water, we're going to add an acid. Concentrated sulfuric acid. Works well, and heat. This heat is applied when we have secondary and primary alcohols, not if we have tertiary alcohols. No heat, just room temperature. Okay, so I'm taking a strong acid, no water. Just if I have a strong acid that's not diluted in water, reaction is going to take place fairly quick, and that hydroxyl group is just going to be taken away. So the hydroxyl group is taken away, and the double bond needs to form where? In the middle of the chain somewhere. If that double bond forms to the left, why does it form to the left? Well, the carbon on the right has got 3 hydrogens bonded to it. The carbon on the left's only got 2. So that one will lose a hydrogen. This one will lose one of its hydrogens. So there's also a hydrogen that comes off, and that makes water. And that's your primary product. And this is your secondary product. The primary product is the more stable one. It's where Zaitsev rule is applied. And the secondary product is just the double bond forms on the other side. But you're not going to worry about this one. You only worry about the primary product. So we have dehydration of alcohols, dehydrohalogenation. We take away the hydrogen and the halogen. In this one, we take away water. Last one. Okay, this one wasn't part of my notes. Dehalogenation. So you start off with a single bond, and we have 2 halogens. There's 2 chlorines, and then we just add heat to that. And then the acid comes off, the polar molecule comes, hydrogen and chloride comes off. Okay. Hydrohalogenation of saturated compounds can also undergo elimination reactions by becoming unsaturated, losing 1 halogen and 1 hydrogen atom. This example, the atom of hydrogen chlorines are eliminated. This is an elimination reaction. It's called dehalogenation. D what? Halo is the group 7 element. We take that one away. And for the double bond to form, another hydrogen must also be taken away, and that's dehalogenation. Okay, we have 15 minutes left. We have finished now just with an overview on all your reactions. You'll have notes on this, but I want you to just think of your reactions in an overview. And the overview is quickly like this. Addition reactions, we start with a double bond, we add with a single bond. Substitution reactions, we start with a single bond, we end with a single bond. Eliminate, we start with a double bond, and we end with, start with a single bond, we end with a double bond. And then all of them are pretty easy because you can substitute things or eliminate things or add things. But there are two difficult ones, and that is when in both of them we are either substituting or eliminating a group 7 element like bromine or chlorine. The substitution one is the one that's going to take slower. That is the one that we're adding a base that is diluted in water. So that's to substitute the bromine or the halogen, any halogen, for alcohol or hydroxyl group. So you form an alcohol by substituting. The other one is where we start with the same alkyl halide, and we're adding a strong base that is not diluted. And that one just eliminate the hydroxyl group and a double bond will form. And the other difficult one is where we dehydrate. We just add acid and take away the water, take away the alcohol, and a double bond form. So those two elimination reactions are quite tricky because one of them looks exactly like a substitution reaction, and the one of them you just add acid and the water comes off. Okay, those are the two that you can get confused with. Right, 10 minutes, sorry. 10 minutes left. Any questions on the work you're doing at the moment?
I have a question with the dehalogenation.
Yeah.
I want to go back to the halogen that was taken away. I don't think I understood properly on why.
Okay.
That halogen was taken away.
Right. So we're adding a strong base like sodium hydroxide. And what will happen? Remember, sodium hydroxide consists of a sodium ion that is charged +1 and a hydroxyl group which is -1. Are you aware of that? Yes. Hi. Are you aware of that?
Yeah.
So this sodium ion will attract that chlorine because chlorine is negative. And it will actually just go and steal that chlorine. So what happens is we have therefore sodium chloride that comes off as a product. But that leaves that chain with a non-bonded carbon there. That carbon there's a bond, but there's no product, or there's nothing on that bond. Okay, I don't want to draw in all these hydrogens. It takes a lot of time. So this is the problem here, that bond there. Now, if we have concentrated base that's not diluted in water, the reaction will take place very quick and nothing will be replaced on that bond. So that bond must either form this way, making a double bond between those two carbons, or it must go this way and make a double bond between those carbons. So which double bond is going to form? Well, the one that has the least hydrogens on the beta carbon. So this one's got 2 hydrogens, this carbon, and this carbon's got 3 hydrogens. So the one with the least hydrogen is going to lose a hydrogen. And so the double bond is going to form there. That hydrogen is going to come off and it's going to bond with that hydroxyl group. So that sodium just steals that chlorine and then there's an extra bond. So it's either going to substitute or it's going to form a double bond. So if there's a strong base, not diluted, it's double bond, not substitution. If it was a strong base and it was diluted in water, then we would have had a substitution reaction. So this is a difficult two, those two that looks exactly the same. Does it help a bit, good sir?
You know, it helps a lot.
Okay. Any questions on the work you're doing at the moment? Otherwise, you name
Honor.
this compound. What do we have here? Anyone? Companies. You're too quiet. Name it. What is this? This is a carboxylic acid name.
Carboxylic acid is
Okay, name. How many carbons?
4.
4 is bute.
No,
There's
it's
only
pro.
single bonds. So it's butane, but we cut off that, so it's butane. It's butane, but we cut off the E for pronunciation. So it's butane acid or butanoic acid. The carboxylic acids are really easy to name. Why? If we have one carbon, there's our carboxylic. Okay, not allowed to write the hydroxyl like that. You must make another bond there. There's one carbon acid. One carbon is meth. So this is methanoic acid. Methanoic acid. Guess what will 2 carbons be? What is 2? F.
Yes.
Ethanoic acid. Okay. Anyone? 3 carbons. 3 is propanoic acid. 4 butanoic. 5 pentanoic. Hexanoic. Heptanoic. Octanoic. Huh? Non-noic. What's 9 again? Non-noic. 10. Well, you're not going to get 10. It's going to go up to 5 or 6 max. 10 is deck. Okay. So your acids are very easy to name. What about what's the difference between a ketone and an aldehyde? A ketone has a double bond somewhere in the middle of the chain. That's a ketone. And an aldehyde, it's got its double bond at the end of the chain. Aldehydes are very easy to name because you cannot have the double bond anywhere but at its starting carbon. So the carbon has got a double bond always as number 1. So that's 1, 2, 3, 4. So what's that? Butane. Just butane, but we're going to cut that off. What is an aldehyde? What's that in English? Nol. Is that butanol?
Ethanol. Yeah, butanol.
Butanol.
Yes.
Okay, so it's butan, and then is it AAL or ALE in English?
Al.
Or butanol.
Yes.
So aldehyde is a L in English. So that's
Yes.
butanol. So you get what? Methanol? You can't get methanol. Yeah, well, yeah, strictly speaking, you get methanol. Ethanol, pentanol, propanol, butanol, pentanol. Well, the ketone doesn't have the double bonded carbon at the end of the chain. So it's either number 2 or number 3 or whatever. And this one, you just number so that the double bond is the carbon with the double bond is the lowest possible value. And in English, that's an ONE or ONE.
It's only ON.
It's an ON. Okay, so this is just what? 4 carbons, which is bute, tan, 2, oops, that's not 2, on. Butane 2 on.
Yes.
My
Can
one
use pardon, Kuta?
is an E. One, like a one.
I can't
Like in English. When I look at it in English, butanol, butane to on.
Yes. Is that wrong? No,
At least the span.
I
It's
cannot.
not wrong.
What name would you give it?
No, it's not wrong. I'm just saying the spelling. It's on one with an E.
I don't understand. You're breaking up.
Really. I'm saying the one in the end. The one in the end, it has an E in the end.
Oh, so it's an own.
Yeah.
Okay, that's what I was asking. So it's ketone, so it's an own. So it's butan to own, not on. But aldehyde is an L, not an ale.
Yeah.
Okay, sorry, I got that wrong. I thought it was on, but it's ketone. It's the same as Afrikaans. Just the number, the naming is slightly different. So it's butan to own because it's a ketone, and aldehyde is just an L. Yeah, I just missed that E. Okay, so it's not difficult. The naming of the last stuff that we skipped on the naming isn't difficult. It's the easiest naming. The alcohols are the hardest to name, and then double bonds and other substituents can be a mixture of difficult. The thing about ketones and aldehydes, you don't get them. There's no reaction with ketones and aldehydes that you learn. You only have to compare boiling points and like viscosity of ketones with alcohols and others. That's the only thing why you need to know ketones and aldehydes and to name them, obviously. Okay, then we're going to go. I'm slightly worried that you're not sending me any questions on homework that you're doing or work that you're doing. So that tells me one or two things. One, you're either not doing enough work. Two, you are brilliant and you know everything in the book or every answer of the questions you've got. Or you've got the memo with you. You've got your facilitator's guide with you and you've got all the answers ready. Okay. So I want us slightly to move towards not only teaching, but also answering questions. Is that good? Is that good?
Yes.
Yes, that's what I want, because then it's easier for me to exactly know what you're struggling with. Good. See you next week.
Thank you.
My pleasure. Bye-bye. Bye. Good sir.
Bye.